My second example appears like this: double integral of the function sine of x plus y by 2 into cos of x minus y by 2 dA over a triangular lamina with vertices at origin 2, 0 and 1, 1. So let me first try to describe my region. That is 0, 0. This is 2, 0. And this would be the point 1, 1. So the region on which we want to evaluate this double integral appears like that. Now, because we have taken up the problem, it is better we also label the diagram in all respects. Without any confusion, this base, because it is aligned along the x-axis, will have the equation y is equal to 0. This line which passes through 0, 0 and 1, 1 should have the equation y is equal to x. Because origin satisfies this equation, 1, 1 also satisfies this equation. The equation of this line can be determined as x plus y is equal to 2, because 1, 1 satisfies this equation, 2, 0 also satisfies the equation. Even otherwise, using school math, you can find out the equation of the line joining 2 points. So this is the region of integration. So are we going to change the variables? That's a big question. Let us see the function. Definitely, it is not a problem that can be handled by the weak hearts. So you need tremendous experience to handle this function if you do not want to change the variables. So I will not think twice. I will change my variables because I'm not happy with the complexity of this function, and how this region behaves with respect to that is a very big question mark. So we'll not waste time on that. I'll introduce two transformations. The transformations are very natural. I'm going to introduce a variable here. I'm going to introduce another variable there. So we choose u is equal to x plus y by 2 and v is equal to x minus y by 2. So the immediate gain will be, this becomes sin u into cos v. So therefore we can see that the difficulty is coming down. But don't stop here. You find out the Jacobian dou uv by dou xy, which is a determinant having partial derivatives of u in the first row, partial derivatives of v in the second row. Now, ux is to differentiate u partially with respect to x. You get 1 plus 0 by 2. So that would make it 1 by 2. Next, uy, differentiate u partially with respect to y. 0 plus 1 by 2. That is another. Then we go to vx. Differentiate v with respect to x, you get 1 by 2. And differentiate v with respect to y, you get minus 1 by 2. So just expand this, you get minus 1 by 4, minus 1 by 4, which is minus 1. So don't get worried, a negative Jacobian will come, technically that's there, but I'll tell you how to basically make it understandable. So what is the meaning of this number? It means the area element du dv in the uv reference frame will be minus half times the area element dx dy in the original domain. But because this is an area element, that's an area element, and even this is an area element, area elements are connected to each other, but you cannot have a positive area on one side and a negative area on one side. Therefore, we use a modulus symbol there for the Jacobian. So du dv is equal to half dx dy, which would give me dx dy is equal to 2 times du dv, 2 times du. So you can see the usefulness of the Jacobian, how it has entered the problem. So how do we now go ahead? Now the region is the same, but because of the transformation, there may be some sort of geometrical changes there. Either the region has changed its shape or it has changed its orientation. Something is about to happen. So let us figure out that. So corresponding to y is equal to 0, the mapping rules, y is equal to 0 from the diagram will make u is equal to x by 2 and v is equal to x by 2. U is equal to x by 2 and v is also equal to x by 2. Eliminate x from these two equations and you will get u is equal to v. U is equal to v is very similar to x is equal to y. So this must be a straight line through the origin, equally inclined to both the u axis and the v axis. Then I take y is equal to x. When I take y is equal to x, I will find my second equation is convenient. V becomes x minus x by 2, that is a 0. So I will get v is equal to 0. Finally, when you have x plus y is equal to 2, I find this equation is convenient. I will get u is equal to 2 upon 2, which is equal to 1. So I get u is equal to 1. Fine. So here we are. I'm now drawing an exclusive reference frame involving the variables u and v. Now, v is equal to 0 stands for the u axis. U is equal to v or v is equal to u stands for the line which appears like this, inclined at 45 degrees to both the u axis and v axis. And then u is equal to 1 would be this vertical line. So that point would be 1, 1. This would be 0, 0. And this would be 1, 0. So call this R dash. So the region R is transformed to another right triangle which looks like this. So if I want to evaluate that double integral, sine of x plus y by 2 into cos of x minus y by 2 dA would be identically equal to the double integration over R dash over this domain into sine u, because x plus y by 2 is u, multiplied by cos v, because x minus y by 2 is v. And dx dy, which is the original dA, is now 2 times du dv. So you can see how Jacobian has come into the play. The rest is all very simple. You have to just fix the limits for this region. So if I call this an RU region, u varies from 0 to u is equal to 1. V varies from 0 to v is equal to u. So this would be integral 0 to 1, integral 0 to u. These two can be pulled out. Sin u cos v, and because these are the limits for v, the order should be dv times du. Don't think this is a complicated integration. It is very simple because you integrate with respect to v. So only this gets integrated, this remains constant. Apply the limits, and then you go for the next level of integration. So I did this evaluation part for you, but the purpose for which I started this segment is over. I have taught you through 2 examples how Jacobians are useful in transforming variables in double integrals. A good practice in this segment will make you a complete student in all respects. Of course, you will have to be basically good at geometry and the integral calculus of 2 variables.